This is a lecture on bracket algebra, the fifth in the series. The essential features of the previous lecture 4 are as follows. The inner product or overlap is the product of bra with a ket. Bra A into ket B is in fact the product of row into column, and this generates a number complex in general. The inner product bra A ket B is the dagger of the inner product bra B ket A, and the inner product bra B ket A is the dagger of the inner product bra A ket B. Norm or length of ket A equal to column A1 A2 is denoted by the symbol A between two vertical bars on either side. It is under root the inner product of bra A with ket A and turns out to be under root mod A1 square plus mod A2 square. For ket A equal to column A1 A2 A3, the norm of ket A is under root mod A1 square plus mod A2 square plus mod A3 square. Ket A and alpha times ket A have same direction. They carry the same information. They differ in length, which is insignificant. Bra x ket phi represents the space wave function phi of x. It is in fact the projection of ket phi state vector along ket x. Bra p ket phi represents the momentum wave function phi of p. It is in fact the projection of ket phi state vector along ket p. The integral representation of bra phi ket psi is the integral from minus infinity to plus infinity phi star of x psi of x dx, and in the process we get the relation the integration minus infinity to plus infinity ket x bra x dx equal to unit operator I cap. If ket 1 is column 1 0 and ket 2 is column 0 1, then the inner product bra I ket j is Kronecker delta ij. And if ket 1 is column 1 0 0, ket 2 is column 0 1 0, ket 3 is column 0 0 1, then the inner product bra m ket n is Kronecker delta mn. Here I, j, mn are dummy indices or run indices. Let us now start our discussion on what we mean by the term orthonormalization. The term orthonormalization consists of two terms, orthogonality and normalization. We first discuss orthogonality. Orthogonality is making two basis unit vectors perpendicular or orthogonal. This is x-axis, the unit vector along which is x cap, also called e1 cap, and this is the y-axis, the unit vector along which is y hat, also called e2 cap. This is the origin. It is a 2D space. Now x cap dot y cap is 0 and y cap dot x cap is also 0. These relations can be rewritten as e1 cap dot e2 cap equal to 0 and e2 cap dot e1 cap equal to 0. This means x cap and y cap are perpendicular. In other words, e1 cap and e2 cap are perpendicular. Let us introduce dummy indices ij, each of which runs over numbers 1 and 2. We can recast these two relations as ei cap dot ej cap for I not equal to j to be 0. We get back the relations putting I equal to 1, j equal to 2 and I equal to 2, j equal to 1. This is the condition of orthogonality of x cap equal to e1 cap and y cap equal to e2 cap. We now discuss normalization. It is fixing the length of basis unit vectors, preferably to unity, that is mod of x cap is 1 and mod of y cap is also 1. So that x cap dot x cap is 1, y cap dot y cap is 1. In terms of e1 cap and e2 cap, we rewrite the relations as e1 cap dot e1 cap equal to 1, e2 cap dot e2 cap is 1. In terms of the dummy indices, we rewrite these relations as ei cap dot ej cap for I equal to j is 1. Combining the orthogonality relation and the normalization relation, we get ei cap dot ej cap equal to Kronecker delta ij. This is called orthonormalization relation for two basis unit vectors x cap equal to e1 cap and y cap equal to e2 cap. Putting back 1 and 2 for the dummy indices I and j, we get back the four relations from here. Suppose this is the axis, x cap equal to e1 cap, this is y cap equal to e2 cap, and this is z cap equal to e3 cap. This is the origin. It represents the 3D space. We first take up orthogonality. Dot product between unit vectors are equal to 0. This means that x cap equal to e1 cap, y cap equal to e2 cap, and z cap equal to e3 cap are mutually orthogonal. Introduce I and j as dummy indices, in whose terms we can rewrite the relations as ei cap dot ej cap for I not equal to j is 0. Now we take up normalization, which is setting mod x cap equal to 1, mod y cap equal to 1, and mod z cap equal to 1. In other words, x cap dot x cap equal to 1, or equivalently e1 cap dot e1 cap is 1. Y cap dot y cap is 1, or equivalently e2 cap dot e2 cap is 1. Z cap dot z cap is 1, or equivalently e3 cap dot e3 cap is 1. So length of x cap or e1 cap, y cap or e2 cap, and z cap or e3 cap is unity. We can write these relations as ei cap dot ej cap for I equal to j to be 1. Combining the orthogonality relation and normalization relation, we can write ei cap dot ej cap equal to Kronecker delta ij. So x cap equal to e1 cap, y cap equal to e2 cap, and z cap equal to e3 cap are orthonormalized, that is orthogonal plus normalized. The orthogonality relation for vector A and vector B is expressed through the dot product, namely vector A dot vector B equal to 0. This means that vector A is perpendicular to vector B. This is vector A and this is vector B, and the angle between them is 90 degrees. This means that the projection of vector A along vector B is 0 and that of vector B along vector A is 0. We now discuss orthogonality of two kets, ket A and ket B. Just as orthogonality of two vectors is expressed by vector A dot vector B equal to 0, similarly, if bra A ket B is 0, this would imply that ket A and ket B are orthogonal or perpendicular to each other. If bra A ket B equal to 0, then bra B ket A is also 0. Bra A ket B is the projection of ket B along ket A, and bra B ket A is the projection of ket A along ket B. So projections or components are 0. Ket A and ket B are independent of each other. So vector A dot vector B equal to 0 and bra A ket B equal to 0 are conditions of orthogonality. Let us now address a question. Are ket 1 given by column 1 0 and ket 2 equal to column 0 1 orthogonal? The answer: we find bra 1 and bra 2 from ket 1 and ket 2. So bra 1 ket 2 is 0 and bra 2 ket 1 is 0. So ket 1 and ket 2 are orthogonal. Another question: are ket m equal to column I1 and ket n equal to column 1i orthogonal? The answer: finding bra m and bra n from ket m and ket n, we find bra m ket n to be 0. So is bra n ket m. So ket m and ket n are orthogonal. Next question: are ket A equal to column 1 I0 and ket B equal to 0 minus I1 orthogonal? The answer: bra A and bra B are obtained from ket A and ket B respectively. Bra A ket B is minus 1, that is not equal to 0. Hence, ket A and ket B are not orthogonal. Next question. Are ket 1 equal to 1, 0, 0, ket 2 equal to 0, 1, 0 and ket 3 equal to 0, 0, 1 orthogonal? Answer. Finding bra 1, bra 2 and bra 3, we find that bra 1 ket 2 equal to 0, bra 2 ket 3 equal to 0, bra 3 ket 1 equal to 0. So ket 1, ket 2, ket 3 are all orthogonal. We next discuss normalization. Consider a vector I hat plus 2j hat. Call it vector A. Magnitude of vector A is under root 5, which is not equal to 1. So vector A is not normalized. To reduce length of vector A to unity, we divide by length A equal to under root 5 to get vector A divided by under root 5, that is 1 by root 5 into I cap plus 2j cap. This we define as vector B. Clearly magnitude of B is 1. So vector B is of unit length. So vector B is a unit vector and can be renamed as B hat. We now proceed to discuss normalization relation for kets. Normalization is in fact fixing the length to unity in general, and this is referred to as normalization to unity, that is setting norm to 1. Consider ket A equal to A1 A2, bra A equal to A1 star A2 star. Then bra A, ket A is mod A1 square plus mod A2 square. So norm of ket A is under root bra A ket A equal to under root mod A1 square plus mod A2 square, which is the length of norm of ket A. And it is not unity, that is ket A is not normalized. Let us divide ket A by norm of ket A to reduce length of ket A to unity. This gives ket A divided by under root bra A ket A. Let us define this as ket B. Check the norm of ket B. It is indeed 1. So ket B is normalized to unity. So ket divided by the norm of ket is a normalized ket. Only normalized kets are considered in physics and quantum mechanics in particular. Normalized kets are kets of unit length. Kets have direction. We call them ket vector analogous to unit vector. Let us take up a question. Is ket A normalized? The answer. We find bra A from ket A and then the norm of ket A, which is 1. So ket A is normalized. Another question. Is ket A equal to column matrix 1I normalized? The answer. After finding bra A, we proceed to evaluate the norm of ket A, and it turns out that the norm is under root 2, that is not 1. So ket A is not normalized. Let us divide ket A by norm of ket A, that is under root 2, to get 1 by under root 2 into the column matrix 1I. It is normalized. Call it ket B. Let us check. We can find the norm of ket B to be under root bra B ket B to get 1. Another question. Is ket A equal to column 101 normalized? Answer. We can find the norm and we see that it is under root 2, that is not unity. So ket A is not normalized. Let us construct ket A divided by its norm and call it ket B. Do a check. Let us find the norm of ket B and it really turns out to be unity. So ket B is normalized. Another question. Normalize ket A equal to 1I1. Answer. We first find the norm of ket A and it is under root 3. Then we construct a new ket B as ket A divided by norm of ket A, that is ket A by root 3. The norm of ket B turns out to be unity. We shall call it a day after discussing what we mean by orthonormalized kets. Consider two kets, ket A and ket B. If bra A ket B equal to Kronecker delta AB, then ket A and ket B are orthonormalized. Let us give example of orthonormalized kets. For ket 1 equal to 1 0 and ket 2 equal to 0 1, the bra I ket J equal to Kronecker delta Ij, then ket 1 and ket 2 are orthonormalized. If ket 1 is 1 0 0, ket 2 is 0 1 0 and ket 3 is 0 0 1, then bra M ket N is Kronecker delta Mn and ket 1, ket 2 and ket 3 are orthonormalized. Question. Check if ket 1 equal to 1i, ket 2 equal to I1 are orthonormalized. Answer. We check normalization. Norm of ket 1 is found to be under root 2, not unity, so ket 1 is not normalized. We normalize ket 1 by dividing it by its norm root 2 and redefining the new ket as ket 1. So ket 1 equal to 1 by root 2 into column 1i is normalized. Norm of ket 2 is also found to be root 2, not unity, so ket 2 is not normalized. We normalize ket 2 by dividing it by its norm root 2 and redefining the new ket as ket 2. So ket 2 equal to 1 by root 2 into column I1 is normalized. We next check orthogonality by finding bra 1 ket 2 that gives 0. So ket 1 and ket 2 are orthogonal. Conclusion. Ket 1 and ket 2 are orthonormalized since bra 1 ket 1 is 1, bra 2 ket 2 is 1, which indicate normalization, and bra 1 ket 2 is 0, bra 2 ket 1 is 0, which indicate orthogonality. Hence bra M ket N is Kronecker delta Mn. The last question we would address is the following. Verify if ket 1 equal to 1 0 minus 1, ket 2 equal to 1 1 1 and ket 3 equal to 1 minus 2 1 are orthonormalized. The answer. We find bra 1, bra 2 and bra 3, the Hermitian conjugates of ket 1, ket 2 and ket 3 respectively. Check normalization. Norm of ket 1 is not unity and hence ket 1 is not normalized. We normalize it and redefine the normalized ket as ket 1. So ket 1 is 1 by root 2 1 0 minus 1 is normalized. Norm of ket 2 is not unity and hence ket 2 is not normalized. We normalize it and redefine the normalized ket as ket 2. So ket 2, which is 1 by root 3 1 1 1 is normalized. Norm of ket 3 is not unity and hence ket 3 is not normalized. We normalize it and redefine the normalized ket as ket 3. So ket 3, which is 1 by root 6 1 minus 2 1 is normalized. Let us check orthogonality. The value of bra 1 ket 2 on calculation is 0. Bra 2 ket 3 is 0 and bra 3 ket 1 is also 0. So ket 1, ket 2 and ket 3 are orthogonal. Hence the kets ket 1, ket 2, ket 3 are orthonormalized. That is bra M ket N is Kronecker delta Mn. This relation includes the orthogonality relations corresponding to M not equal to N as well as normalization relations corresponding to M equal to N. Let us end up with a question. What is linear vector space? We will discuss it in the next lecture 6.